Do, do, do,
No, no, that's
do.
fine.
Everybody see the screen okay?
Yep.
Hey, how about that? This is working out pretty good. And of course, as usual, when I put the people up there, it sort of blocks out my left side, so I got to move things over a little bit. Good evening. My name is Pete Hermes. I've got a brief presentation on carbon stars, a lot of it rooted in a recent completion of the Astronomical League's Carbon Star Observing Program, which was kind of interesting, kind of fun to do. I think often, we always look for things in the sky that provide some interest or also provide a unique vision or look, I guess. For some of us that, especially under 8 inches of aperture, being unable to pull in, the fine detail on galaxies and nebula. We're stuck with a lot of stars and the planets, but still, you don't get that detail on the planets. But for the most point, of course, when we're looking at stars, they're point sources. We aren't going to see much more than that, other than occasionally we can see a little color in some of these stars. And ostensibly, most of the carbon stars are red, and I'll discuss it, or different shades and hues of red, and I'll discuss that. But that's what drove me towards this, completing the AL's program, and some of the things I learned from it, and I wanted to share some of that. And as usual, it's always a privilege and a pleasure and honor to present for you all. On the opening slide, you see probably one of the more well-known carbon stars or red stars, colored stars, La Superba, which is why Canum venaticorum, that's pretty readily seen. I think I'm trying to remember. I think even in binoculars, this will show up for a lot of folks. Even 10, for sure 20s, but I think even in 10-power binoculars, this one will show up. Anyhow, come on, let's go. Oh, I know what I have to do. Click. There we go. Okay, so just in a matter of introduction, I'll talk a little bit about the definitions and some of the characteristics that are specific to carbon stars, how they form, or at least what are some of the mechanisms. I'm not going to get real down in the weeds on this one. Trying to keep it so that I understand what I'm talking about. A little bit about the classification, protocols, and procedures for carbon stars. A few things on observation here again, attributed primarily or focusing primarily on, how to see color in the stars, or at least the stars that manifest with some color, some of the things that can be done so that you can appreciate this aspect of viewing. A little bit about here again, the Astronomical League's Carbon Star Observing Program. And when I have a few examples, and you'll see that after when we get into the observation, you'll see some of my a couple of excerpts from my log, and you get an idea of what I did towards completion of the Astronomical League program. And then, of course, references and questions or comments will be more than appreciated at the end. If I make a faux pas or there's something really, uh, I say something really wrong, please stop me and speak up and let me know what it is. We'll fix it and move on. Okay, as far as a few basic characteristics of carbon stars, for the most part, and like I say, there are always exceptions to the rule, but for the most part, and just about in all cases, and surely some recent discoveries or some discoveries to come in the near future may provide some additional information. But for the most part, most carbon stars are variable stars. They're late type red giants, most often, not always, but generally is the case. And they're by the name carbon stars. The reason being is because they have excess amounts of atmospheric carbon molecules, typically seen through, spectroscopy used to look at these stars. I mean, yes, we can see the color, but as far as looking for the lines specifically attributed to some of these elements and some of these molecules, there's elemental carbon, carbon monoxide, cyanogen, methylidine, and zirconium oxide. And those are the predominant molecules that present in carbon stars and thereby present with their basic coloring or hue. For the most part, carbon molecules will act as a filter, limiting the wavelengths, blocking those at the other portions of the visible spectrum, the yellows, the blues, and greens, however, allowing the reds to come on through. Here again, longer wavelengths like orange and red are going to pass through the carbon star. If you want to call it atmosphere, I mean, stars for the most part do have atmospheres, a little bit different than, what the planetary bodies might have, but they do have, the area immediately surrounding the star. High levels of carbon monoxide, utilize most of the oxygen. So thereby, there's going to be low, which may result in low concentrations of elemental oxygen and elemental carbon in some cases. Typically, there are two main methods or mechanisms by which carbon stars generally exist. One is you have carbon dredged up from the core by convection, which is merely matter or material towards the core of a star or deep inside of a star. Because it is hotter and lighter, generally it will move up towards the outer surfaces of the star, up into the atmosphere. Mass transfer between binary classical carbons and main sequence or dwarf companions is another. These are the two main mechanisms. You'll see they're referred to, and I'll talk a little bit more about that. The classical, which is carbon dredged up from the core by convection, and then mass transfer between a binary system where you have a classical carbon and main sequence or dwarf companion. And basically, that larger star is pulling, of course, from the dwarf or the main sequence. With respect to what's going on, as far as it's kind of hard to nail down any history, but for the most part, carbon stars, and they weren't necessarily called that immediately, but basically they were first discovered as what was referred to at the time as a Type 4 star by Father Angelo Secchi, who was a Jesuit and was did most of his work in Italy, a lot with some of the Vatican science outlets and some of the observatories that were available at the time. And I think just about all of them, all of his work was on the Italian peninsula. But for the most part, you don't, there are numerous papers that have been written. There are numerous people that have worked looking at carbon stars, maybe even specializing or focusing on that. But generally, you don't see too much of an attribution with respect to certain individuals. There doesn't seem to be any one researcher or astronomer focusing on research work in carbon stars. Going back to the classical carbon star, with regards to formation, like I say, atmospheric carbon, core to outer limits by convection. And typically what you see, and there are two types, they have the CR and the CN types. You'll see some helium fusion, and the diagram is pretty simple and self-explanatory for the most part, but you have uh, two helium atoms or nuclei that come together, they form beryllium, and then you see beryllium forms with another helium nuclei, and then we end up with the carbon. And this is what's referred to as the triple alpha process. Basically, the helium nuclei, if I remember correctly, is what's considered an alpha. And for the most part, we're not worried about the electrons here. We're just concerned about the nucleus of the atom, because that generally, yeah, you may have different ions, but that generally derives, the characteristic elemental components of any given substance. And so you can very easily see two heliums combining and then beryllium combining with helium to form a carbon atom, which is about halfway along the sequence of elements that are created in normal stellar processes. Typically, we don't see anything up through beyond iron, which is what, 26, I think. So this is not quite halfway through the periodic table to that point, but they are fairly common. And one other aspect, especially with respect to classical carbon stars, is generally they're longer period variables. And you're going to see there's a little bit of variation. There are some differences in the periods of some of these variables. But for the most part, you'll see these classical types are of the longer period. I would say in excess of probably 50 days on up into 5 years. A lot of them you will see are probably in the, I'm going to say, probably in the 100 to 300 day range, approximately. And of course, there are higher and there are lower. As far as the non-classicals coming back here again, it is a mass transfer in a binary system of a classical carbon star main sequence or dwarf. The main sequence or dwarf becoming, I'm sorry, I had that backwards. The main sequence or the dwarf becoming the carbon star. Okay, not the larger main star in the system. These typically have the classification or designation CJ and CH types. In some cases, these is where barium stars will sometimes come. The non-classical formation of a carbon star could result in a barium star. And these are also referred to as extrinsic carbon stars because one star is drawing matter from another one. In other words, external to its system, where it only makes sense intrinsically in the classical form, you actually have that carbon being dredged up from the central or lower limits of the star. Now, this is where I lose part of my slides. Oh yeah, for the most part, most carbon stars are classified in spectral class C. C system replaced the earlier Harvard R and N classifications, which is what they were known as probably in the earlier parts of the 20th century. However, you will still see some designations that will hold on to the previous classifications, but mostly most of the carbon stars are going to be classified CR, CN, and CJ, as I previously referred to, especially with respect to their distinctive coloring. Okay, as far as viewing, taking a look at carbon stars, actually observing them for the most part, color sensitivity is a problem at night for most of us, and especially those of us who are a little bit older. Oh, that I wish I was a little bit younger, because even though the problem would still exist, it probably wouldn't be as detrimental as I experience now. But basically, when we night adapt, uh, we're setting our eyes up basically so that we're sensitive to, the least amount of color change. And of course, we try to avoid those bright lights so that we have the opportunity to be able to resolve and see with some degree of clarity the objects we're looking at through the eyepiece. Well, what this results in is a little bit of a detriment with respect to being able to perceive colors. For the most part, our color vision is diminished when we're night adapted. In some cases, that's a good thing. In other cases, it's not, because certainly if you're looking at colored stars, that's not necessarily a good thing, because you might miss especially some of the more subtle aspects of some of the colored stars, carbon stars or even blue stars for that matter. And so certainly, in some cases, it can be resolved by having, you know, looking at some low light and actually reducing some of the night adaptation so that you're able to make those color perceptions. Uh, Not really recommended if you want to be able to, pick up some of the fine detail or, strong clarity in the objects you're looking at. But what it does do is it does bring out some of those colors. Typically, when I was observing, if I was having a problem detecting the hue from a particular star, it's not that I'm necessarily going to blind myself with a bright light, but I might look at a light off in the distance that wasn't necessarily blinding, just to reduce some of that night adaptation and try to return some color sensitivity, where I get a little bit more rod base, which is what picks up the color in the on the back of your retina, getting the rods to work a little bit more, which they don't generally work as good. If you notice, when you're looking at things at night, ideally good, night adaptation, you're able to pick out objects with a fair amount of clarity and see detail and contrast. But what you do lose, and even when you're looking at things, outside of a eyepiece, and not necessarily observing through a telescope, is that often you will have problems detecting colors. And of course, here again, it's one of those things, as we age, that's one of those things that degrades a little bit more than most people. So, and this is why it can be a little difficult. These are one of the, colored stars are some of the neatest things to look at, but it does take a certain amount of effort with respect to night adaptation. Now, don't get me wrong, some stars, carbon stars included, some blue stars, they still show up regardless, because they have a good solid color. They're not, especially if you don't have a faint one. Generally, the brighter the star or the more contrast that's available in your field of view, generally the light perception is going to be better. Okay. And of course, the fainter the star, the more difficult it becomes, to the point where, in some cases, and I know I was looking at a very red star, but I'm just not picking it up. Like I say, a couple of the things I try to do is, reduce a little bit of my night adaptation, or one of the other things, I tried was, just look, like I say, reduce some of that night adaptation by looking into a light. even increasing the magnification, although I found, in some cases that work, but not in all cases. Just trying to pick out a little more detail because unfortunately, trying to increase magnification would reduce my field of view and therefore reduce the contrast that I might have in a field of view in order to see that color. So it certainly helps a lot if you have other stars nearby to help you, perceive those colors, because sometimes it can be very, very subtle. Sometimes not necessarily the case. You look at something like La Superba, that's not a problem trying to perceive that color. And of course, there's no set, color. You take a look at this color diagram, uh, the different hues that carbon stars will come in, and they will run the whole gambit. I think typically, when you look at this, you're going to see, reference red certainly is uh, attribute that you'll see assigned to carbon stars. Crimson, garnet sometimes. A lot of these other ones, not necessarily. They're varying level. Scarlet. You might see 4 or 5 of these attributed in descriptions, and certainly it's something that the Astronomical League uses in describing some of the objects that are included in their carbon star program. But for the most part, clearly about 15 or 6 of these, you don't see them referred to so much. They're just varying hues, but it is a way in order to be able to, assign at least some level of redness, I guess is the best way to put it. And in a lot of cases, it isn't necessarily always red. I mean, some of these carbon stars will appear orange, in some cases distinctively orange, although that is difficult to pick out. And especially in some cases yellow. But remember, typically carbon stars are going to restrict or diminish those wavelengths of light from getting through, so they can be rather difficult to pick out at times. I want to go back. Yeah, this was the second item on this slide. I just went back one. You'll notice I always put my personal phonetic soundings for these words, but the Purkinje effect, which deals with that luminance sensitivity shifting to the blue end of the spectrum in low light. Reds appear darker than other colors, and that's another thing that will happen with respect to becoming night adapted or trying to see color at night. Certainly, that's an issue to be taken into consideration. So moving on, here's a couple of examples of some probably real well-known carbon stars. I think most of you have probably seen these. For the most part, a lot of these, in some cases, are even visible with the naked eye. Most assuredly, like I said, through binoculars, but through a telescope, even low power, they're rather interesting things to look at. Heinz Crimson star. This was discovered, in the middle of the 19th century by J.R. Hind, thereby its name. But it's a well-known variable, very popular. And you'll see the 5.5 to 11.7, that's the variation in the luminance of this particular star, and the period running anywhere from 418 to 441 days. It's 1,350 light years from our solar system, and the luminance of this particular star is almost 6,700 times that of our sun. Well, nothing far-fetched to really gather here, because you remember we said most of these are red supergiants or red giant stars. And of course, you'll see a rather low temperature for this, given the nature of this particular star. It's under 3,000 Kelvin. This is basically the same slide. You can see here, this was my observation of this particular star that I did for the Astronomical League's Carbon Star program. Some of the notes that I'd put into it, Doug's seen this before, trying to identify some of the other stars. There were a lot of, dimmer stars in here. And actually, I mean, this color by itself would have shown up fine just by nature of this particular star. Like I say, some of the fainter ones are a little bit more difficult to perceive, the variations in the hues. This, I think, if I remember correctly, like I say, it was distinctively not so much, there was that crimson color, which is sort of like, it's not that deep dark red, but something a little bit brighter, I guess is the best way I can describe it. U Cygni is another one. And the interesting thing about, and the reason I included this is because you'll see it's in the upper left-hand portion of this particular photograph. There's actually an eighth magnitude white star just to the upper left of U Cygni. And so it's kind of interesting. That helps bring out, to me, I think it brings out that color, or it's easier to see because you have some contrast. Now, I will tell you, of course, and you'll see it because I have my sketch of this. Of course, I didn't see this many stars, and this is I mean, it's a wide field, but still there's a lot of detail in there. I think I picked up at most 10 if I have that many. But here again, we have a similar star with respect to the variation in its brightness, uh, roughly sixth magnitude all the way up to 12, similar to Heinz 463 days period, uh, 32.6 light years away, only 10 parsecs, so it's relatively close. The luminance in this particular star is 368 times that of our sun. A little bit hotter, 38, just under 3,900 Kelvin. But when you take a look at this, and of course, I want you to make sure that you pick up the similarity between this photograph and my sketch. Not really, but you'll notice here again, the brighter star, which is actually, of course, it's blocked for me, is SAO 49479, and that was that eighth magnitude star. And you can see I have probably about 10, I don't know, 7, 8, 9, 10 stars in here, but this color was relatively easy to make out. One of the things I also included here was basically just my summary. And typically the way I would put together my observations for this particular program, the little, the nice formatted 7-line summary of the particular object, where it was viewed, date and time, of course, what it is, what sort of equipment I used, of course, transparency and viewing. And here's another thing too that I didn't really mention: transparency and viewing uh, contribute a lot to how well you're going to be able to see uh, whether or not if it has any color at all, and then being able to distinguish the various hues in some of these stars, especially as they might be described. One of the things, and I'll bring this up now, Astronomical League puts together, they have a nice guide, and it's something that they have to purchase. And this was a no-brainer for me. Of course, it's only about a $10 or $15 item, but it had a lot of good information about this particular program and what to do so that you could get the most out of it as far as being able to complete the program, but also enjoy the viewing that you were doing. And of course, the last item I include is power magnification. But going back to transparency and seeing, it goes without saying, as with just about any object you look at, you're going to be able to see it better, pick out those details, pick out the color better, of course, when you have, better transparency and good seeing conditions. If you have a little bit of wind affecting your seeing, or, the atmosphere is a little bit unstable, and then most assuredly, if you don't have a good dark spot, or you've got a lot of light pollution, or you have something else obscuring your vision, of course, that's going to diminish the experience you're going to have in this particular case. Finally, another example, this isn't something I looked at, but it's kind of interesting how some of these will show up in this case. Yusefi is pretty much, there's a lot going on in this particular photograph here, but it gives you an idea that sometimes you can be looking at some of these red stars. And of course, this is, Herschel's Garnet Star, another very, very well-known red star or carbon star. Here, the variation isn't as great. It's only about 3.5 to 5 magnitudes, but a significantly longer period, 860 days, plus or minus 50, 2,800 light years away. Very bright star. Estimates of luminance anywhere between 283 and 340,000 times the luminance of our sun. And, probably medium range for most carbon stars, 3,540 degrees Kelvin. But you can see there's a lot going on, and this is a very wide field photograph of a lot of the surrounding area. But just to show that in some cases, there are carbon stars that will sort of sit out there by themselves, and if they're faint and you have to use a fair amount of magnification to sort of pull them in, you lose a lot of the field, which I think, if anything, and it's probably true of any colored stars, but I think it's just as true of carbon stars. You get a little bit more out of them when you can view them with other stars in the field. Fainter or brighter makes no difference. I think it helps, for one thing, I think it helps bring out some of those colors. A couple of things about the Astronomical League's program. Like I say, I showed you the guide. I think it's all of about 25 pages, but it has a lot of good information explaining carbon stars. Of course, they have their list. I'm trying to remember, I think the program, as is typical of most Astronomical League programs, calls for one to view. Oh, wait, there weren't that many. No, there's more than that. 28. Trying to remember the numbers on it, but it escapes me right now. No, there were 100 objects in the program, so you go through them. But the neat thing about it too is, the Astronomical League and its guide. You can see I'll just show you sampling of this. You know, a number of their pages will have about 6 or 7 of the objects, and they provide a very good description, location, coordinates for it, and a description. And certainly, like I say, sometimes it was disappointing because I wasn't getting the same. I wasn't able to view the same thing, and so. But in a lot of other cases, it's kind of interesting when you see it and the color really stands out. It's kind of fun to do. But anyhow, like I say, there's 100 carbon stars. They range in magnitude from 4.5 to 13.9, and of course, this is varying uh, throughout that time. Most are in the 7 to 8 range, so they're very. I think they're very accessible with respect to. I think I did most of these with my 5-inch reflector. I did a few with my 8-inch SCT. But certainly, of course, the darker the conditions, the better. And I think for the most part, I did just about all of them on my back deck at the house. So I don't have the darkest conditions, but they're fairly dark. I mean, as Doug has told me, the Milky Way, depending on the right nights, is generally visible from my backyard. But in some cases, I still have a lot of neighbors that like to keep their garage lights on. But anyhow, I'd say periods ranging from 2 to 600 days. So, in some cases, and I noticed this, especially with some of the shorter term stars that had a wide range. You can see these. I picked up on a couple of them, not most of them, maybe 2 or 3 of them, where I'd look at them, maybe 10, 15, 20 days later and recognize or remember a variation in the brightness. Not too often, though. Wider ranging carbon stars, yellow to orange. Generally, you're going to see the reds at the minimums. That's just the nature of these particular stars. Stars will appear redder as observing time increases. So sometimes, spending a little more time at the eyepiece, averted vision, but avoiding the light unless absolutely necessary. The quick glances, these are some of the other tricks that are used, that we all use to try to bring out a little bit of detail, especially color, with respect to some objects. Those are my references. Oh, I always put this in there, but you'll notice, you don't see typically, most of the carbon stars are going to be AMs way over on the right side of the Hertzsprung-Russell diagram. And probably a little bit up as far as absolute magnitudes. Here again, that's going to vary. They're variable, so they're moving up and down, but pretty much in that M range and a little bit more to the right. Thank you very much. Are there any questions, comments, or otherwise?
Quick comment.
Yes, sir.
We have that carbon star